Before we get to our analysis, let's make sure that we had similar observations for part 1 of reactivity of metals with water. When we had sodium, or when we saw the video of sodium and water, we saw that it caught on fire. We saw that it gave off lots and lots of heat, and that ultimately there was a small explosion. For magnesium, when we put that in water, we didn't see anything happen. It was kind of a dud, so I'm going to put nothing there. And then for calcium, we did see that the piece of calcium went from being silver to being white. It gave off heat. Now, it was pretty hot to the touch. I couldn't hold the test tube for very long, but in terms of comparing heat of sodium versus the heat of calcium, I'd say that sodium wins. So calcium gave off heat, but not nearly as much as sodium. And there was lots of smoke. And if I had to rank these in order of reactivity, I would say that sodium is the most reactive, calcium is the second most reactive, and magnesium comes in third place. Now for part 2, where we took the metals and added hydrochloric acid, let's jot down or make sure that we have the same observations. My number 1 was magnesium. When I added hydrochloric to magnesium, I saw that there were lots and lots of bubbles. It almost looked like the piece of magnesium was foaming and kind of dancing around in the container because it was so reactive. It was dancing around. So lots of bubbles. It did give off heat, and by the end it was completely dissolved. My number 2 was zinc. This one, I didn't see heat. I didn't see smoke, but I did see that the piece of zinc was completely covered in bubbles. My number 3, and it could be a fluke, it could be because the iron was in lots of small pieces instead of just one big piece. So it could have been the pieces of metal moving around, or they trapped a little bubble, but I did see 1 or 2 bubbles come off of the iron. I saw it, so I'm going to write it. It could be nothing. For my aluminum and copper, I really didn't see anything happen, so I'm not going to give them a ranking. I'm just going to put nothing next to both of them. All right, and our last part 3 of our lab, was over density. I'm going to use the data that my last class period collected, but I want you to fill in your data table or have the numbers from your particular trial. So the mass for my class was 13.94 grams. The initial volume of water before I added the lead was 5.0 milliliters. And the volume of water after adding the lead was 6.3 milliliters. So volume of the sample of lead, if I use my water displacement method, 6.3 minus 5.0, I have 1.3 milliliters that came from the lead. And if I want to calculate my density, I'm going to take mass, 13.94 grams. I'm going to divide by volume, 1.3 milliliters. And when you type that in, I'm rounding to 2 significant figures. I got 11 grams per milliliter. So I'm going to put my density there. 11 grams per milliliter. Okay, now we're ready to analyze our questions for part 5. What might be a reason for the difference in behavior between magnesium and calcium when placed in water? So I want to take a look at where magnesium and calcium are on the periodic table. I see that magnesium is here. Here's my magnesium, and here's calcium. So we saw that calcium was definitely more reactive than magnesium. So it looks like as we move down a group, reactivity increases. What might be a reason for that? So we had a few different factors that affect periodic trends. I know as I move down, the number of protons increase, but also the distance between the nucleus, that positively charged nucleus, and those valence electrons. Magnesium is in period 1, 2, 3. Magnesium is in period 3. So that magnesium nucleus, this positively charged nucleus, has 1, 2, 3 energy levels around it. Whereas that calcium nucleus has 4 energy levels around it. 1, 2, 3, 4. So the distance from the nucleus to the edge of the electron cloud for calcium is longer than that of magnesium's. And because of that, we can say that the attractive pull or effective nuclear pull of calcium is less effective than that of magnesium. So because calcium's nucleus doesn't have as good of a pull on its valence electrons, it must be easier to remove those electrons. Also, I noticed over here for sodium, I didn't see any of the other metals over here lose their electrons or react because it's not safe to do in a school environment, but it does say that as I move down, they do get progressively more reactive. And I do know that as I move down a group, my atomic radius increases, so the larger the atomic radius, the more reactive my metals are. All right, let's go back. Number 2 says list the 5 metals from most reactive to least reactive. Use data from your lab to support your answer. Well, we already ranked them earlier. We said that sodium came in first place and was the most reactive. Calcium comes in second place. It was the second most reactive. Magnesium comes in third. It didn't react with water, but it definitely reacted with hydrochloric acid. And then in fourth place, I'm going to put zinc. After zinc, the other metals, honestly, they really didn't react very much. I'm not going to list them at all. I'd say those were all least reactive. Number 3, in general, is there a relationship between locations of metal in the periodic table and their relative activity? Explain why. So let's take a look, and we've already compared sodium, calcium, and magnesium, but let's see where zinc is. Zinc is at the very bottom of my reactivity. So let's see where zinc is. I see that zinc is all the way over here. So it looks like as we move in this direction, I know that, let me change colors here. Actually, let me just erase some of this here. Okay, so I know that as I'm moving from here to here, I did see that reactivity definitely increased. Sodium is more reactive than magnesium. I also see that zinc is all the way over here, and it was the least reactive out of the metals that we saw do something. So it looks like as we move in this direction to the right, reactivity decreases. I also noticed that as I moved down this group, so if I compared magnesium to calcium, calcium was definitely more reactive than magnesium. So as I move down a group, reactivity increases. And my explanation has a lot to do with that effective pull of the nucleus. The closer the nucleus is to those outer electrons, the stronger that attractive pull, which means those electrons can't be removed. So what exactly was happening when those metals were being added to water, or when those metals were being added to hydrochloric acid? Well, our metals were losing their last valence electron, or in the case of calcium, its last 2 valence electrons. So calcium, because it must lose 2 valence electrons, it has a lower reactivity than, say, sodium that only has 1 valence electron to lose. It costs less energy. All right, let's go back and make sure that we've hit everything on our analysis. Do the results of your density lab support your estimate? So in your pre-lab, you estimated what the density of lead might be. We saw that for silicon, the density was 2.33 grams per milliliter. Then we skipped, who did we skip? We skipped germanium. We didn't do the density of germanium, but we did have the density of 10. And for the density of 10, SN, it was 7.28 grams per milliliter. And I had you estimate what is the density of lead going to be. And hopefully you saw that as you were moving down that group, density should increase. So I was looking for a number that was bigger than 7.28. When we measured mass and volume and calculated density of lead, we got a density of 11 grams per milliliter, and this does in fact support our estimate that density increases as we move down a group. Number 5, what can you conclude about reactivity of metals as you move down a group, or as you move down a column or group in the periodic table? So I can conclude as I move down a column or a group, so on the periodic table, As I move down the group, so as I move in this direction, I know that reactivity increases. Number 6 says, what can you conclude about the reactivity of metals as you move across a period? And I can conclude that as I move across, as I move in this direction, we said reactivity decreases. Number 7, arrange each set of the following metals in order from least to most reactive using conclusions you just made. So we have francium, sodium, and cesium. Let's pull up our periodic table. Let me see if I can delete all my writing here. Oops, that's not what I wanted to do. Hooray! Okay, so we are going to compare. We have francium here, we have sodium here, we have cesium here. It says to compare their reactivity. I see francium is all the way at the bottom. It would be the most reactive. And sodium, even though we saw that gigantic explosion compared to the other metals, it would be the least reactive out of my 3 that were listed here. So order of reactivity from most reactive to least reactive, francium would be first, cesium would be second, and sodium would be last. Now we have rubidium, gallium, and francium. So let's take a look at those. My rubidium, RB, where are the others? I already forgot who they were. Rubidium, gallium, and francium. So rubidium, there's francium, and gallium is way over here. So here I see that gallium is all the way to the right. I can tell you with confidence that as far over here as it is going to be very, very unreactive. I can still say, so in general, the trend is as I move down this bottom corner, reactivity increases. And as I move to the top corner, reactivity decreases. So I can say that francium would be the most, gallium would be the least, and rubidium would be right in the middle. Francium, rubidium, and gallium. 8, which is the most reactive metal in the periodic table. Our most reactive metal is francium. Would you expect this metal to be found in its unreacted elemental form? Explain. Well, if it is the most reactive metal, would we find it ever unreacted? I think the answer to that is no. Because it's so reactive, it is always found in combination with another metal. Or another metal or non-metal. More than likely, non-metal. Last one, conclusion. When elements are organized in the periodic table, various trends appear. Describe the reactivity trends that you learned about from this lab. Use your knowledge of effective nuclear charge, distance between nucleus and valence electrons, electron shielding, and electron-electron repulsion to support the trends you notice in reactivity. It must be at least 5 sentences. So I know that as I move down the periodic table, the effective nuclear charge decreases. And if the pull of the nucleus decreases, then it doesn't require very much energy to remove those electrons, which means reactivity is going to be very high. I know that effective nuclear charge as I move to the right increases. The pull of the nucleus gets stronger, which means more energy is required to remove those electrons, so metals on the far right are unreactive. The distance between nucleus and valence electrons, we talked about that as well. We said the further the distance between that positive charge and the outer valence electron, the weaker the pull of that nucleus. It's all about the pull of the nucleus. The further away the electrons are from the nucleus, the easier it is for that electron to be removed by another species. Electron shielding we really didn't talk about, but I know as I move down a group, my number of electron shields increase, so number of completed energy levels. The more electron shields there are, the weaker the effective pull of the nucleus. I know as I move across, electron shields do not increase, they remain the same, so electron shielding is only going to be as I move down a group. And electron-electron repulsion. So the more electrons a substance has, the more repulsions there are and the easier it will be to remove an electron. So more electrons equals easier to remove those. So as I move down a group, because francium, for example, has a lot of electrons and a lot of electron-electron repulsions, it's easier to remove those electrons than, say, sodium that's higher up in group 1. Okay, you need at least 5 sentences. Make sure you have everything nice and neat written down, and you'll submit your analysis to today's assignment, and then you'll take the metal reactivity post-lab quiz, which is the exit ticket for today.